Swayam Prabha. Digital India. Educated India.
Today we shall be starting with the ninth and the last module of this course. In this lecture we shall be starting the discussion on some case study of the Linux operating system. Okay. So, of course, we shall not be going into the very details of how Linux works internally, because it is quite involved and complicated. We shall be giving you some kind of an overview based on whatever we have discussed in this course so far. So, what is there in Linux, how it works with respect to the different modules of the operating system, and so on. Okay. So, let us start with the very basics. What is Linux and how did it originate? Now, many of you who are familiar with operating systems, the Unix kind of operating system, know that Linux, the way it looks, the way it feels, is very much similar to the Unix operating system, which was in existence since long. Since the 70s, the first version of Unix emerged, and then there are versions of Unix which were proposed and which were supported by various industry giants like IBM, Sun, HP, and so on. Now, Linux is a product of the open source revolution in software. You can say Linux is not just one operating system, but rather it is a family of operating systems, and that is based on a common kernel which is called the Linux kernel. So, the idea is that at the core you have the Linux kernel. This is the basic thing, and on top of it there is a layer which you put, which you call some Linux distribution. Now, there are various Linux distributions exist, they are available. Many of you may be familiar with this. Some of these are Red Hat, Debian, Mandrake, Ubuntu, and there are several more. They are basically a layer which is put on top of the Linux kernel, which is mostly common. There are versions of the Linux kernel, and this operating system is today available on almost all platforms. And talking about the origin of the name Linux, how this name Linux originates. Okay, some people argue that Linux comes from the acronym Linux is not Unix, but it is not exactly true. The first person who started developing the Linux kernel, his name was Linus Torvalds, and this was very similar to Unix. So, the first name of the author and this Unix taken together, the name Linux emerged. So, this is basically the origin of the name. And here the penguin that you see, this is the logo of the basic Linux kernel. So, this logo indicates that this is a Linux operating system. Okay. Fine. Now, talking about the structure of the Linux operating system. So, we discussed earlier that an operating system is divided into several layers. So, in Linux you can distinctly talk about 5 different layers. At the lowest level we have the basic hardware. So, when you talk about the basic hardware, we are talking about the processor, the CPU, the memory, secondary memory, the different IO devices, all these things taken together constitute the hardware. That is the platform on which all our programs are running. On top of it you have the Linux kernel. So, this next layer, which is called the Unix operating system, basically this is what the kernel is. This is the basic kernel or the central important routines that an operating system should have, that is part of this layer. So, this includes the essential routines on process and memory management, file systems, input outputs, etc. So, all these things are taken care of by this layer, and this is kernel. This is doing something, this is, you can say, directly interacting with the hardware, and quite naturally these routines must run in the kernel mode. So, they must not be running in the user mode, because there will be some privileged instructions for accessing the hardware that will be part of these routines. Okay. But on top of this kernel or this basic layer, you have the standard libraries, standard system libraries which any program can access or use. Typically these libraries include calls like open, close, read, write for file system, fork, exit for managing processes, and so on. So, any application or any program which is running at a higher level, they can access this library interface. So, at the lowest level you have the system call interface, meaning that these routines of the kernel can only be accessed through system calls, syscalls. So, the mode will change from user mode to kernel mode and the routines will get executed. But the standard library I am talking about, this is the so called library interface. On top of which there are a set of programs which have been written, which are standard utility programs which help the users, like the shells that you use, bone shell, cone shell, bash. There are many shells that we use which interact with the user through the terminal. There are various editors available under Unix, compilers, debuggers, many routines are there. Everything here, they fall under the standard utility program and they provide a standard user interface. And all user programs, they typically interact through this layer. But however, if you are a sophisticated programmer, you can also directly access this layer, the standard library. Many a time we do, but most of the time we use the standard utility program, the user interface layer. Okay. So, this is basically the structure of the Linux operating system, how it generally is layered. And of course, the upper three layers, they work in the user mode, they do not include any privileged instructions. Okay. Fine. Now, talking about the utility programs, that are provided. So, there are a number, there is a good set of such utility programs which are provided under Linux. They fall under several categories, like firstly there are a set of programs which help you in file and directory management, like you can create a file, you can copy a file, you can create a directory, you can rename a directory, rename a file, lot of things are there. So, all these utility programs fall under the first category, file and directory manipulation commands. There are something called filters, like for example, I give a command, I get some output, but I do not want all the output, I want to filter it, I want to see only a subset of the outputs, or I want to see the output in a slightly different format. So, I include a filter. That means, filter is like a layer where the output of some program you are running is coming and the filter is presenting the output in a different way. This is what filter is. And there are many filters available. For example, sort is a filter where the output is displayed in sorted order, alphabetic order. Then you can have some utility like global replacement grep, which can check the presence of certain words in the output string and can only display words which contain that string, and so on. In the third category, we have the utilities which help you in development of programs like editors, compilers, debuggers, and so on. And when you are creating some text, like you are preparing some text, you are formatting it, you are converting into some PDF or some other format. So, you have a set of text processing utilities. Using which you can create a document. Of course, there is a host of tools which aid in system administration. You know that in every large installation there is a system administrator who have to manage the system. Who are the users of the system? You want to create a new user account, you want to check how much space a current user is occupying. If required, you can add some space. You can take a backup of the file system onto secondary storage. So many things are there. Okay. So, that is system and there are a set of general utilities. So, we group it under miscellaneous. So, these are the different kinds of Linux utility program, the categories which are present. Now, a few of the utility programs are shown here on the slides. These are very common. We use these utility programs very commonly in our day to day use when you interact with the operating system, Linux operating system. Like the first command is cat, which is the short form for concatenate. Like if I give a command like cat some file name, let us say xyz.txt. So, what will happen? This file xyz.txt, whatever is the content, that will get displayed on the screen. That is our standard output. So, it is called concatenate. Concatenate this file onto the screen. If I want more than one file, I can also do that, xyz.txt, abc.txt. So, one after the other they will get displayed. So, one or more files you can display on the screen on the standard output. Then you have the copy command. In Linux the copy is cp. So, you can give a command like cp, the source file name, whatever file you want to copy, and then the destination file name where you want to copy the file name. So, in source and destination you can give a path with folders and subfolders. Similarly, you can rename a file, that the command is move mv, you are moving a file. So, the syntax is similar to copy, move old file name, new file name. So, it is something like this, move old name, new name. So, here again you can use folders to specify the old name and new name in case they are not present in the current working directory. And there is a very powerful command called grep, global replacement, where you can search a file for a particular string or for some particular pattern. Okay. So, wherever that pattern is available, that will be displayed on the screen. So, it is a very useful command. If you want to search for something among a large number of files, you can use the grep command. And ls will list all the files in the present directory. And there are many options or flags in ls. You can display the list of files in various different ways. Suppose you want to display all the details of the files, the typical command is ls -l. -l is a flag. Then if you want to delete a file, the command is rm or remove, remove file name. Normally when we create a program, when you write a program in C or any other language, we have to first create the program using an editor, using a text editor. So, one of the very common text editor in Linux is vim, that is a text editor program. Now, after you create a C program, let us say, you have to compile it to generate the executable. So, cc is the name of the compiler. So, cc is another command you can use to compile a program. So, I talked about filter. Sort is one of the filter. It sorts a set of lines in dictionary order. Dictionary order means lexicographic order. A comes first, then B, then C, in that order. In terms of directories or folders, there are commands like you can create a new directory by the mkdir command, make directory. You can remove a directory by using rmdir command, remove directory, or you can change the current working directory by using this chdir, change directory. So, these are only a small subset of the common utility programs that we use. There are many more. Okay? Fine. So, talking about the Linux kernel, that is the basic layer that is running on top of the hardware. The most important components are shown here. So, you have components that manages the processes, like you know already, we discussed earlier, that a new process can be created using the fork system call. Similarly, you can terminate a process. So, process or thread creation and termination, that is one important thing under this module. There are many processes running, how they are allocated to the CPU scheduling, some suitable algorithm would be running there. I mentioned that Linux uses some version of multiple queue scheduling. Okay. So, that CPU scheduling algorithm is there, and you can send something called a signal from one process to another, that is done through a signal handler. So, signal handling is also maintained by this component of the kernel. Okay. Next, coming to memory management, which is also extremely important. Of course, Linux implements virtual memory, any modern operating system will implement virtual memory, and it uses some version of demand paging. The concept of paging is here. So, paging, page replacement algorithms, all these things are handled by this component. And there is another important thing called page cache. You recall in our previous module we said that when you access some data in the disk, some secondary memory, if you want to read something, not only the requested word or byte, the entire block of data gets transferred to memory. Now, the question is, where do you store the block into memory? Suppose in memory we are already using paging, you are using virtual memory, let us say the page size is 4 kilobytes. So, you select your disk block size in such a way that that is also 4 kilobytes. So, that when you temporarily load a block into memory, you can exactly fit it into a page. That is what is meant by page cache. Instead of keeping a separate area in memory where all the disk blocks will be temporarily stored, you can keep them in a regular page as part of the normal virtual memory system. That is very flexible in that case. Okay. And then you have the components that handles all input and outputs. Now, in Linux means in fact this came from this concept came from Unix itself, it was there in Unix also, that all the IO devices they are treated as files. So, you open a file, you read a file, you close a file. Similarly, you can open an let us say input device, read something from the input device and close the input device. So, to the user, suppose you are writing a program, it does not matter whether you are using a file or an IO device. For example, as I said, you can copy a file from by giving a source file name and a destination file name, right. Suppose in the destination file name, instead of a file name, I give something /dev/ let us say TTY01 and some name. This TTY01 may indicate my screen, my terminal. So, when you are copying some file to the terminal, as if you are displaying it on the screen, you are copying it to an output device. So, the output device is also treated as a normal file. So, in Linux you have on the upper layer the virtual file interface, which integrates the different kinds of files that are there under it, and they provide a unified interface to the user program. All interaction with the file system will be through the VFS, that has a uniform interface, open, close, read, write, like that. But with respect to the file systems, underneath under the VFS there are three kinds of things. One will be something called character device drivers, which handle one character at a time, like keyboard, like your terminal and so on. So, these are the terminals you can say. You have the network interface. So, over the network some packets are coming, your computer is sending some packet to some other place. So, that is the socket interface, and the regular file system. You have the regular file system where the actual files are stored. So, all these IO devices has some utility or program that will handle them, they are called device drivers. Device drivers are part of the Linux kernel that handles different kinds of IO devices. So, you have the scheduler and other things all are included after that. Okay. So, this is the basic structure. Now, regarding the process part, well, this we have already discussed earlier, that in Linux when you or Unix, when you create a new process, the command or the function that you use is the fork. You invoke a fork system call. When you are booting the Linux system, initially there is a single process which gets created automatically, that is called the init process, and init calls fork to generate other processes. So, when you are switching on the system, initially only one process gets created automatically during boot time, all other processes. So, you can see at a time there are hundreds of processes running. So, all other processes will be automatically created by that initial process by calling fork system call. Now, the way fork works, just to recall, you can define an integer variable, let us say PID, process ID, that is the name you have given. You call fork, it gives a return value. So, fork creates another copy of the running process, this we have already discussed. So, there will be a parent, there will be a child. So, the value of PID will be different for the parent, the value of PID will be different for the child. So, whether it is parent or child, that you are checking in this if statement. First is you check whether the fork was successful or not. If it returns a negative value, then it is an error condition. You display some error message, you print it to the standard error device, that is typically the terminal, and you return -1, you stop your program. Otherwise, if you see that the value of PID is some positive value greater than 0, which means this is the parent process. So, whatever parent code you want to write, include it here. Otherwise, if PID is equal to 0, because less than 0 you have included, greater than 0 you have included, else means it is equal to 0. If it is equal to 0 means it is the child process. So, whatever code you want to write for the child process, that you will include here. This is how basically you write a program to create a new process in Linux. Okay. Now, I said a process in Unix can send some so called signal to another process, like you have a process 1, you have a process P2, a process P1 can send some signal to another process. Now, these signals, there are different kinds of signals, and these signals have some signal ID 0, 1, 2, 3, 4, there are some numbers given to the signals. But in one of the header files, each of these signal IDs are given some names. So, instead of those numbers, you can also use the names in your program. So, here some of the common signals are mentioned. One is sig abort. Sometimes you want to stop a process forcibly, you can send a sig abort signal to that process, the process will be aborted and something called a code dump will be generated. Code dump means whatever is the content of the memory during the execution, that will be dumped into a file on the disk. So, later on you can open the debugger, load that file and see what is happening, because your program might not be running or working as desired, you want to find out what is happening. So, you can send a sig abort signal to the running program, get a code dump and then you debug whatever is wrong there. Okay. And you can set an alarm, sig alarm, like you can write a program or process where you check if there is an alarm, then do this, otherwise do something else. So, sig alarm signal, whenever it is sent to a process, that process will be triggered by that alarm signal. If it has written a code that if there is sig alarm then do this, then that part will be activated. Okay. Sometimes you see when you compile a program, whatever program you are writing in C, C++, whatever language, that gets translated into machine code. Now, every instruction in the machine code starts with an operation code or opcode that indicates what kind of instruction it is: add, subtract, compare, jump, whatever. Now, every such opcode has a unique code, 0, 0, 1 combination, but there may be some 0 1 combination which are not currently assigned to any of the operations. Those are invalid codes. Some opcodes may be invalid. Suppose due to some reason there have been some corruption in the memory, you are trying to execute an instruction which is an invalid instruction, then automatically the running program will generate a illegal signal. It will be sending to the operating system. Okay. Sometimes the program is running on the terminal, it is running, somehow it is not coming out. We can forcibly stop by pressing Ctrl C on the keyboard, Ctrl C. If you press Ctrl C, then a SIGINT signal gets generated and sent to that process, and that SIGINT program will interrupt that process and stop it. Okay. Sometimes you want to stop a running process altogether. It was running, but you want to forcibly stop it. You can send a SIGKILL signal. SIGKILL signal, if you send it, then the process will be killed. Then we discussed pipe earlier for inter-process communication. Suppose a process has written something into a pipe, but on the other side there are no other process which is reading from that pipe. So, that will generate a SIGPIPE signal. Again, in a program where you are using pointers, pointers means memory addresses, due to some error in the program, maybe your pointer calculation has gone wrong, you are trying to access a memory which is an invalid memory area, which is outside your process address space. If you try to do that, your process will be generating a SIG-SEGV, segmentation violation signal. Sometimes whenever you are running a program, there is some error, you get a message segmentation fault, that is due to this SIG-SEGV signal that was generated. And of course, there are a couple of signals which are not specified that what it is for. As a user, you can define their functionality. These are called user defined signals, and signals are a very powerful way for inter-process communication, informing a process what to do, what not to do, and so on. Okay. So, these signals are available in Linux. Talking about process management, here some of the system calls are shown. This fork already I have mentioned, the first one, the fork system call. This is used to create a new child process. So, initially they will be identical. So, after you check the value of PID, there may be a branch. The parent may want to wait for a child process to terminate, then you can use this wait PID system call. This wait PID system call can wait for a particular child process to terminate. And we had seen earlier, a child process can call an exec system call to load another program and run overlaid on it. So, it will be replacing a child's core image and load a new program on top of it. That you can do using some exec family of system call. Exec V is just one of them, exec LP, exec LE, lot of variations are there. Then you can terminate a process execution by calling the exit system call. Now, regarding signals, since we have not discussed signal in detail, there are some function calls available for signals. These are all available: sig action, sig return, sig proc mask, sig pending. Okay. They have some specific functionality, and as I said, a process can send a signal to some other process, and the function to send it is called kill. Well, this name is a little misnomer. Kill does not mean that you are trying to kill a process. Kill means you are trying to send a signal to a process whose process ID is PID, and which signal you want to send? That signal number you mention here. Okay. So, a process can send a signal to another process by using the kill system call, and of course, you can set the alarm by calling the alarm system call. When that alarm reaches 0, that clock reaches 0, and sig alarm signal will be generated. And you can pause execution of a process till a signal hits that process, it will again wake up. So, these are some of the process management system calls that are available. Now, all of us, when we use a Linux operating system, we open a terminal, we type a command. Opening a terminal means we are running a shell. Modern day operating system, the default shell is bash, BASH, but there are many other shell, corn shell, bone shell, C shell, many shells are there. Shell is basically a program which reads commands from the user and executes that command. So, here what I have shown is that very rudimentary structure of how a shell looks like and how a shell actually runs. You see, first is an infinite loop, while 1, this loop runs continuously. In a terminal, you see that you display a prompt. So, on the terminal window, something is displayed, either greater than or something. That means it is asking the user to type a command. So, you are calling a function called display prompt, which is displaying that prompt on the screen. Then you are reading a line, the user is typing something, enter, that line is read. That line will contain, see, for example, you give a command like, let us say cat file name xyz. So, your command is cat and xyz is a parameter. So, you call a function readLine, which is reading the command as well as the list of parameters that you are giving after that. Now, whatever command you have typed, you fork, create a child process and ask the child process to run that command. The parent will be continuing to wait to read the next command. So, you create a new process by fork. First, you see that whether there is an error, PID is negative or not, you flag an error message. You can choose to continue, you can choose to stop, whatever you want. But if it is a parent process, PID is greater than 0, you do not do anything, just wait for the child to finish, because child will be running that command. You call this wait PID command, and these parameters indicate that you are asking the parent process to wait till the child terminates. Else, here is the child process, you are executing the command. So, you are running the command which was specified along with the parameters that was specified. So, cat xyz, you call execv, you will be calling cat, it will be overlaying on top of the child and that will be executed. And after this is done, again while loop, the next command, the parent will go back to wait for the next command. This is how a simple shell works, right. Now, talking about process scheduling, as we mentioned earlier, Unix or Linux uses some kind of a multi-level scheduling queue structure. There are number of queues where some processes may be waiting for its chance to get the CPU, and each of these queues may be having different levels of priority. Okay. Depending on the type of processes, the priority may change. Now, in Linux, the convention is the priority values can be negative as well as positive. So, the 0 value of the priority is considered as a normal priority. Whenever a process is created, it starts with a priority value 0. So, any values greater than 0 means lower priority. Any value which is negative less than 0 means they are of higher priority. This is the convention that is followed in Linux. So, the diagram on the right, some of the example queues are shown. The user priority is 0, this is the priority value 0. This is for some processes which are not that important, like user processes which starts, you can have it started by default at priority level 0, or some process is waiting for a child to exit, that is also assigned a priority 0. But if a process is waiting for some other IO devices, like waiting for terminal output or disk IO something, they may be having higher priority. So, the operating system automatically adjusts the priority value, and as a user you can assign lower priority values to your process, but you cannot assign the other, you cannot make it higher priority, but you can make it lower priority. There is a command called nice. Using nice command you can reduce the priority of your process in case you feel that your process is not that important. If it takes some more time, that is also fine. Okay. Now, the difference between this negative and positive priority values is that the positive values, these are all in the all waiting in the user mode, but the others, the negative values, these are the processes waiting in the kernel mode, they are waiting for the result of some IO operations. That is the main difference. Okay. Fine. Now, I said earlier that when Linux boots, only one initial process gets created automatically, all others gets created through fork. So, here I am just showing you a very sketchily thing. This is the init process with a process ID value of 1. That is the first process which gets created, and it creates other processes by running fork. For example, the first process it creates is something called kthread, that is a thread creation daemon. Daemon means some programs which are running in the background. It has a PID value of 2. So, there are many such other processes which get created one after the other. Like when you see that your user process, you can see that your PID is something 8000 something, that means there are already 8000 processes created before that. Many processes get created, they get terminated and so on. Okay. So, this is just an idea, I am not going into the detail here. Talking about memory management, well, as I said, Linux uses virtual memory, it uses paging. So, suppose I have a process A out here and a process B out here, and in the middle you have memory. In the memory you see everything is divided into pages, equal size pieces. Some of the pages on one side, they may be occupied by the operating system OS, and you know that in Linux or in Unix a process address space is divided into several sections: text, data, heap, stack. So, you see for the process, on one side you have the text, here you have the data, here you have the stack, and heap will grow here if required. BSS is actually part of the heap, you can say. BSS is something which refer to uninitialized data. Okay. So, similar is the case for the other process B, they have also some areas. Now, whatever is the text, for example, text area for this process will be mapped somewhere. They all get mapped. Initially when you do a fork, the text area gets mapped here, date area gets mapped somewhere, the stack area will get mapped somewhere. So, they will all get mapped somewhere in memory. Some memory may be occupied, some memory may be unused. For example, this data and BS, this part is allocated space here. Similarly, this data part is allocated space here, and they will be mapped to multiple pages. This is how mapping is done, and there will be a page table in the middle, as you already know, we discussed it. They will take care of the mapping. Okay. Fine. And in case you want to share something in the memory, there is something in the memory you want to share. So, here you are showing some pages out here or some data out here which the two processes want to share. So, in the process address space you can create, or basically you are creating suitable entries in the page table. so that for process A it is also getting mapped to this same place, process B it is also getting mapped to the same place in memory. So, both the processes are using same part. This is exactly what we saw when we took those examples on shared memory. We can create a shared memory segment, we can attach it to the two processes, that is the basic idea, right. So, you can have sharing in this way. So, in the physical memory there will be some part where the data will be stored, and both the processes will have that part mapped from their address space, and this mapping can be done by suitably setting the entries in the page table. So, those pages will be mapped to those corresponding pages in physical memory. Okay. Both the processes will be getting the same mapping, all right, fine. Now, talking about physical memory management, there are some zones that are defined by Linux. Well, it uses paging, all right. There is one zone which is referred to as DMA zone, one is the normal zone which is mostly used, all the processes which are loaded they use the normal zone, and there is a high mem zone. High mem zone is typically the region which is currently unused. And DMA, for those of you who have studied DMA in your computer organization, DMA stands for direct memory address. Whenever you transfer data between disk and memory, suppose you have your disk out here, this is your secondary memory, you have your main memory out here, this is your main memory. In the middle there is something called a direct memory access controller. So, whatever I said, you can transfer a block from disk to memory or memory to disk. This block transfers, one block here can be loaded into some place in memory. It is the responsibility of the DMA controller. The CPU is not doing it. CPU is just telling the DMA controller transfer this block, and the DMA controller will automatically carry out this data transfer. It can be the other way around also. From here the data can go to the disk. So, DMA zone will be containing those pages which are currently in the DMA operation. So, why this difference? Because DMA transfer is going on, you must not replace those pages from memory, because some operation is going on and DMA controller is doing that, CPU is not doing that. So, if you remove that page from memory, then the entire means IO transfer operation will become wrong. Okay? Fine. So, this is just an overall picture, I am not going into the detail of it. So, you keep track of these three zones. This is your memory map, so where all the pages are mapped and so on. This is your physical memory where those pages are loaded, and this zone descriptor, you maintain lot of information there. So, the operating system, Linux operating system maintains lot of areas about the zones, like what are the free areas, the minimum page number, maximum page number, how many free pages are there, lot of things are there, lot of information are stored. So, we are not going into detail of this description. So, all these things are handled by the operating system, Linux operating system, and these are pretty involved. If you want to go into the detail, the complete details are available from multiple sources. There are very good textbooks available on the internet, also there are some very good resources available. If you want to learn more, you can go through them in detail. Okay. Now, let us come to a point regarding implementation of the page map table. Now, typically this Linux operating system runs on the modern day processors which have 48-bit to 64-bit addresses. So, 2-level or 3-level page table is certainly not enough. You may have to go for 4-level page table. So, Linux supports 4-level page table. So, the complete virtual address is divided into 5 parts. Of course, the least significant part is the page offset within the page, because ultimately you are accessing a page in memory. So, what is the offset within that page? That is the last part, and the other part is the first piece will address a global directory, that is the outer directory, outer page table, some entry in that outer page table. That entry in the outer page table will be pointing to one of the next level page table, because the next level there may be multiple such page tables. It will be pointing to one of the page tables, and within that page table upper directory will contain the offset, the which entry. Similarly, that entry will contain one of the next level page table. Here again there will be many page tables, and middle directory will tell you the offset in this table. Similarly, the last level it will provide an offset, and finally what is stored here, that is your page number. Now, the difference you try to understand, all these levels are stored in memory. So, to access a page, if you want to access the page table, you have to access 1, 2, 3, 4 and finally 5. 5 memory accesses to get the data. So, your overhead has increased, but there is no way out, your address is much larger, you have to do this. Okay? Let us work out a simple exercise problem. Let us take a simple problem. Let us say we have a 4 level page table, there is also a translation look aside buffer, TLB. Some of the recently used pages are loaded in TLB, information about the pages. The TLB access time, let us say, is 10 nanoseconds, main memory access time is 100 nanoseconds. 95% of the time the page is found in the TLB. If there is a page fault, the page is not in memory, it will take 3 milliseconds to transfer the page, and page fault happens 0.1% of the time. What is the effective memory access time? So, this kind of problem we have also seen earlier, but here it involves a 4 level page table. So, what will be the difference? First, let us look at the TLB. So, step by step let us see. First, look at the TLB. 95% of the time the value is obtained in TLB. So, 0.95 multiplied by, so if it is found in TLB, how much time will it take? 10 nanoseconds to access the TLB plus 100 nanoseconds to access the memory. This will be the time that will be taken if there is a TLB hit. But if it is not in the TLB, so it is 0.05, 5% chance. So, 0.05 will be multiplied by what? Not found in the TLB means we have to search the page table. Now, there you can find the page, or it can result in a page fault. So, it says page fault rate is 0.1, 0.1% means 0.001, this fraction. So, 0.999, this is the fraction of time where the page will be found in memory. Now, if it is found in memory, then what will be the access time? First, you have already accessed the TLB for that 10 nanosecond, plus I said you have to access 4 levels of page table and then finally memory. So, 5 memory accesses. So, you will be needing 500 nanoseconds. Okay. But if it is not there in the memory, there is a page fault 0.001, this will be multiplied by 10 nanoseconds, you access the page table 500 nanoseconds and finally you find that the page is not in memory. So, you will have to transfer the page, that will take 3 milliseconds. So, if you add these things up, whatever you will be getting will be the effective access time. So, you see, to make the effective access time close to the memory access time as far as possible, you must make two things. TLB hit rate should be as high as possible, page fault rate should be as low as possible. Both these things are ensured by taking advantage of locality of reference and having a very good replacement algorithm in place. So, replacement algorithm is very important in this context. So, in Linux also, even if it uses 4 level page table, if it can maintain page fault rate at a very low level or TLB hit rate at a very high level, the overhead will not be that much, that significant. In the worst case, you may require so many memory accesses, right. So, with this we come to the end of this first lecture of module 9. Here we discussed some of the basic concepts or basic working of the Linux operating system. Now, we shall be continuing with this discussion in our next lecture as well, where we will see that how some other features of the Linux operating system work. Okay. So, this we shall be discussing in our next lecture. Thank you.